Train data here. In the last video, I went through OLS, ordinary least squares linear regression, as an estimator for the slope and intercept of miles per gallon as a function of weight in the Mtcars data set. And OLS regression is by far the most common because the matrix algebra can differentiate, and also it's just standard. But options exist. You could also do least absolute deviations, least median squares, theil-sen, and plenty of others. And so the purpose of this video is I'm going to go through how to use other estimators on that same data set and then explore the difference. And one major drawback of OLS regression is that it's not robust against outliers, meaning that if you had certain points of high leverage, it could really adjust the slope of the line. And I will demonstrate that. So the first thing I'm going to do is load the tidyverse package so that we could use the tidyverse verbs, and then also the mass, quantreg, and MBLM packages in order to get these other estimators. And then finally I just load library MetBrewer so that I can have colors, just like different kinds of colors. Okay, so the first thing I'm going to do is do lm_fit, which is the LM function from base R, miles per gallon, as a function of weight in the Mtcars data set. And then when I create that object and I look at it, I can see as a specialized list the coefficients for the slope and the intercept. And I can also type COEF in order to get the coefficients for the intercept and the slope, or I can use the brackets to call them by index 1 or 2. And then in order to create the other estimators, what I could do is, for example, theil-sen, I could do from the MBLM package, the function name is also MBLM, miles per gallon as a function of weight, and the data is Mtcars. Theil-sen is interesting. It creates a line in between every single pair of points, and then it finds the median line. So it's sort of a non-parametric technique. There's also least absolute deviations, which is from the RQ function in the quantreg package, miles per gallon as a function of weight, data equals Mtcars. And then also what we can do is do the RLM function, miles per gallon as a function of weight, in order to get least median squares. And each one of these really deserves its own video. I'm really just showing you how to create, how to sort of refactor the code to create multiple models and graph them at the same time, and then explore some of the difference. So RLM, that's least median squares fit, that's what I'll call it. So below, I won't type this all out again. What I did here is I took the coefficients, both of them, for the linear model, theil-sen, least absolute deviation, and least median squares, and I wrapped that in the data.frame function in order to turn that into a data frame. And then I can also use the T function, which means transpose. If you use Excel, you'll write out the word transpose. Transpose is flipping something over the diagonal. It's very common in linear algebra, of course. And so here I transpose it, so I have the intercept as one column and the weight as the other, and each model has its own row. And I can save that to an object, which I might call models. And then also, what I can also do is turn that into a tibble, which gives me the option of creating a column name on that first column, which is currently an index column. And what I can do is type row names equals model. And then finally, what I can also do is rename with in order to get new names, because intercept's a bit weird with the parentheses. Intercept, and then I'll also rename the final column as slope, so it's clear that we're talking about the slope and the intercept. And I'll save that all as models. Okay, now in order to graph them, what I can do is use ggplot and then take labs for the title, just to take it from the top. Labs title equals simple linear regressions. And here what I'm going to do is make it a scatter plot with geom point. And the data here is going to be Mtcars. And the aesthetic mapping will be weight on the x-axis, and the y-axis will be miles per gallon. And finally, I will use geom AB line as my geometry in order to get the slope and intercept. Here, I'm going to have to specify another argument for data as models. And you can feed two different data frames into ggplot if you want different things. They just have to be able to map together. So AES for aesthetics, and intercept, I'm going to say intercept refers to intercept in the model's data frame, and slope refers to slope, and color, I'm going to change the color for each model. And then I'll also make the size 1. And finally, to make use of the Met-Brewer package to add a color here, I'll do scale color manual values equal met.brewer function. And I like to use the Hiroshige palette. And I say 4 because I have 4 different things that I'm creating a color for. And now let's do a ggplot here. And we can see that I've created a graph that has simple linear regressions for least absolute deviations, the linear model, which is the OLS regression, LMS, which is least median squares, and TS for theil-sen. Okay, so I said that OLS regression is not robust to outliers, and I want to show you what I meant by that. So in another code chunk, and I will again type code in between the two backticks, I will do Mtcars, and here I'm going to, I oftentimes like say select from the dplyr function specifically, because select I've discovered is a function that has a common name across different packages. So if you have different libraries loaded, you might run into issues if you in the select function, and also the error messages that accompany those are sometimes not super clear. So here's one way in which you can add data to your data frame. I'm going to say bind rows tibble equals miles per gallon, and I'm going to come up with tibble miles per gallon equals a collection of, I'm going to come up with additional data points to add to Mtcars that are going to really change the slopes of the lines. That's the purpose of what I'm doing right now. Mtcars, additional cars. I'll save this as a new data frame, which I'm calling Mtcars additional cars. And I can always save the object with the right arrow, just like I saved it with the left arrow earlier. So let me pick some data points in this quadrant down here where there's not much activity, and in this quadrant. So these will act as high leverage points that will you know, if you picture the middle here as a sort of fulcrum, it's going to skew the slope of all of the lines, but some more than others. So let me pick some data points. If I choose weight, let's say miles per gallon, I'm going to choose small numbers like 8 and 10 and 12. And then I will also choose big numbers like 30, 32, 34, and I'm going to have those small and big numbers correspond to small and big numbers in the weight category also, like 1, 1.5, and 2, and let's say 5.5, 5.75, and 6. And I create a new data frame, Mtcars, additional cars. And here what I can do is I can just copy and paste my code, but I will change the data frame that I'm reading in so that I'm actually reading Mtcars, additional cars. But I also will need to recreate the models. So I'm getting ahead of myself. Let me recreate the models, all from the Mtcars, additional cars data set. And then I'll graph it again. And here you can see what I did is I added these data points down here. I added these data points up here. And it's dramatically changed the slope of the line of the ordinary least squares linear regression. And also it changed the line of the least median squares, which is interesting, but not so much against least absolute deviation or theil-sen. So if you have data points that you know are outliers, and in particular points of high leverage, which means that it's going to be far on the x-axis to the left or the right, in addition to being an outlier, then you would want to figure out a way to handle these outliers, or else you might want to consider using a linear regression estimator that is robust against outliers. Okay, that's it.